Hello, Math 1224. This is Dr. P with Lesson Launch 702, Comparison Shopping. Take a look at the integral I've written here, the integral from 1 to infinity of 3 sine of t plus 7 over t dt. The question I want to ask and try to answer in this video is whether that improper integral is convergent or divergent. So in other words, if we were to look at the area between that function, the area of the region between that function's graph and the x-axis between 1 and infinity, will that area be finite or infinite? Now, rather than present a graph of this function straight away, which would be pretty revealing, I think, actually, I would rather just think about this analytically and see if we can come up with any function to which we might compare the one that we have here. So find a good function for comparison. Whatever good means, I'll get to that later. For comparison. Alright, so you might ask yourself, okay, look at this function here. How does this function behave as t goes to infinity? After all, we're mostly concerned with how this area is going to behave as t approaches infinity. So if I look at this, I think, okay, well, the denominator has a t in it, so that's going to force the entire thing to converge to 0. That is, the function value itself will converge to 0. I've got a 7 up here, and I have a 3 sine of t. Now, think about how 3 sine of t behaves for just a minute. How does 3 sine of t behave? Well, that is always going to be between negative 3 and 3. The value of that will always be between negative 3 and 3. So what do we know? We know that this function, the value of 3 sine of t plus 7 over t, that is always going to be between 3 plus 7 over t and negative 3 plus 7 over t. And just like that, I've simplified this problem quite a bit. Because if I'm trying to think about the integral of 3 sine of t plus 7 over t, I mean, you might wonder, could I integrate that? Could I just go ahead, compute the improper integral exactly, and use that to determine whether the integral diverges or converges? But let me tell you, you try to integrate this thing, you can forget about it. That sine of t over t there, I don't think there's an integration technique in the world that's going to allow us to integrate that and evaluate the integral exactly. So forget about trying to do this directly just by computation. Instead, let me just X that out. There we go. So instead, we're going to use these bounds. We have a lower bound and an upper bound. We'll call that lower bound and an upper bound. And we're going to use those to analyze whether the integral of this function converges or diverges. So let's just pick one of these to focus on. Let's pick this one over here, 10 over t, and ask ourselves, how does the integral from 1 to infinity of 10 over t dt, how does that behave? All right. Well, I can compute that one directly. That one is going to be the limit. That's the limit as b goes to infinity of the integral from 1 to b of 10 over t dt, which is the limit. And then the antiderivative of 10 over t is, I think that's 10 natural log of the absolute value of t. And since we're only worried about positive values of t, that absolute value is not going to matter too much in the end. But I'm writing it anyway for now. So that's the limit as b goes to infinity of, that looks like 10 natural log of b minus 10 natural log of 1. Well, natural log of 1 is 0, so we're just talking about the limit as b goes to infinity of 10 natural log of b. Now, how does that behave as b goes to infinity? This one's a little bit trickier, but the natural log of b, if I let b be as large as I want, I can make this number as big as I want. For example, if b is, now just hang with me for a second here, if b is, say, e to the 1,000, then natural log of b would be 1,000. If I wanted that value to be 1,000,000, natural log of b that is, I would just let b equal to e to the 1 million. So my point is there's no limit on how big this can get. This will get as big as we want, and the 10's only going to make it even larger. So that limit there, that's infinite. So what we conclude is that the integral from 1 to infinity of 10 over t dt, that diverges, and it does not have a finite value. Okay, so let's step back for a second, because what is it we were trying to do here? We were trying to figure out whether this integral here, the integral of 3 sine t plus 7 over t, whether that integral will converge or diverge. And all I've established right now is that this integral, the integral of 10 over t, is going to diverge. So that diverges. In other words, it's infinite in this case. Okay, so one question we might ask ourselves is, if I know that this integral is smaller than something that's infinite, well, question, what is smaller than infinity? Think about that for a second. What is smaller than something infinite? Actually, this is a trick question because there's a couple of things that are smaller than an infinite area. A finite area would be smaller. That would be smaller, but an infinite area could also be smaller. That is to say, an infinite area could fit perfectly within the area described by this integral here, the integral of 10 over t. So my point is, knowing that the integral of this is smaller than something that's infinite doesn't tell us a thing. It doesn't tell us whether this integral will converge or diverge. So I just want to record that. Right now we have no information. We have no info about convergence or divergence of the integral. I need to give myself a little bit more room to write here. Of the integral 1 to infinity 3 sine t plus 7 over t dt. Knowing that it's smaller than something infinite just isn't enough to help us. Okay, so at this point, I guess we could give up, go home, watch Game of Thrones, and just forget about doing calculus. But you know that's not my style. You know I'd rather solve this problem. So let's look at what we have and see if there's anything here that would help us solve this problem of whether this integral converges or diverges. Well, this bound didn't help us, but what about this lower bound here? That lower bound is 4 over t. Now think about this for a minute. So what about, let's see, pick a new color here. Okay, so what about the integral from 1 to infinity of, sorry, not 10 over t, 4 over t dt. That's what this one was. So this lower bound here. So what about that? Well, what does that do? Well, the integral of this, and I'm going to leave this as work for you to do, but I'm going to say this also diverges. And why does it diverge? The reason is really pretty much the same thing as what we did above. Same reason as above. It's just we're replacing that factor of 10 with a factor of 4. Okay, so what does that mean? So in the big picture of things here, okay, big picture, there we go, bigger picture, okay, there we go. So what that means is that the area described by this function is greater than the area described by this function, which is infinite. So what I've done here is I've shown that for all t, certainly all t greater than or equal to 1, that 3 sine of t plus 7 over t is greater than or equal to, let me make that a little bit neater, greater than or equal to 4 over t. And the integral from 1 to infinity of 4 over t dt, that diverges. Therefore, the integral from 1 to infinity of 3 sine t plus 7 over t dt must also diverge. Because it's bigger. That's because for any b greater than 0, the integral from 1 to b of 3 sine of t plus 7 over t dt is greater than or equal to the integral from 1 to b, I'm going to run out of room here, from 1 to b of 4 over t dt. And because this integral is going to infinity, so this integral must go to infinity as well. Okay, this is an instance of a more general principle. Now I want to tell you straight up what the general principle is, because this is what you'll need to know the most from this section. So we've concluded that the integral that we were thinking about diverges. But here's the general idea. God, my penmanship is still not that good. I think I'm just not lifting up the stylus enough. So here's the general idea. This is called the comparison test for improper integrals. And here's the idea. Suppose that f and g are functions continuous on the interval a to infinity such that 0 is less than or equal to f of x is less than or equal to g of x for all x in that interval. So I'm going to be talking about improper integrals from a to infinity. All right, so suppose f and g are known, they're defined, they're continuous on a to infinity, and we have this comparison here. That's the most important part, really. Then we know two things. Number one, we know that if the integral from a to infinity of g of x dx, if that converges, then the integral from a to infinity of f of x dx must also converge. Okay, now think about why that is. Why would it be that this has to converge? Well, we know that f of x is a function, it's continuous, it's positive, or at least non-negative, and that function's value is smaller than the value of g of x everywhere. Okay, so if the area defined by this integral here, if it's finite, if it has a finite real value, then this has to have an even smaller finite real value, or at least it can't be any more than the value of this. So if this doesn't go to infinity, this can't go to infinity, because this has to always be smaller than this integral. All right, that's the first thing we know. Second thing that we know, if the integral from a to infinity of f of x dx diverges, then the integral from a to infinity of g of x dx must also diverge. Yep. Must also diverge. And again, there's a good reason for that. The reason is, if I know that the area represented by this integral diverges, well, I know that g of x is a function whose value is always greater than that of f of x. So if this is going to infinity, then this has to go to infinity at least as fast, if not faster. So those are the two things I know. We might put that colloquially in a little bit tighter language. The basic idea here is that, number one, smaller than convergent is convergent. And idea number two, let me get a different color here. There we go. Number two, bigger than divergent is divergent. Assuming, and this is for both of them, assuming everything is positive. That's crucial. If we're working with functions that can have negative values, then we need to think a little bit harder about what's going on. Okay, now, the most important thing to notice is the two things I didn't say. I did not say that smaller than divergent is convergent. And that's because certainly an integral that converges is going to have a smaller value than an integral that diverges, because the one that diverges in this discussion goes to infinity. And I didn't say that bigger than convergent is divergent. It is true that something divergent will be bigger than something convergent, but here's what we don't know. We don't know that an integral smaller than a divergent integral move up a little bit there. We don't know that that will converge. It could still diverge. So this comparison test for improper integrals only works when we choose the comparison well. If we look at the example we're working with, oh my goodness, things sort of ballooned, didn't they? That's always the fun thing about this, is that when I'm moving things around, I'm always zooming out, but I always write bigger than that zoomed out text. There's no way to write smaller, so my text starts really small at the beginning and then ends up really big at the end. Anyway, my major point was here. We started out this video by looking at this integral here. In order to be able to say definitively whether that integral converges or diverges, we had to make a favorable comparison. We looked at this function and we compared it to something that I call a, well, I actually just realized I don't have much of a name for it. It's a function that's a constant over t. I don't know what we call it. They're rational functions, but there's rational functions also that are convergent, so that's not a good descriptor for this. Anyway, we looked at this and we said this is essentially a constant over t. It fluctuates. That numerator will bounce between 4 and 10, but it's essentially a constant over t as t goes to infinity. Now, we could have thought at this point, that function, that type of function we're comparing it to, we know, if we've been around these long enough, that these integrals, they're always going to diverge. This one diverged, this one also diverged. So if we know that in advance, we could say strategically, let's look at the lower bound. Let's prove that the integral of this is above something that is known to diverge. Because then, if I prove that this is bigger than something infinite, I will have proven that the integral of this, that is this integral here, is infinite. So in other words, if I'd been doing this with the full advantage of my experience, I would have focused on this comparison first. I wouldn't have messed with the other one. I did that just to illustrate. This is an example of what we can't do with comparison. Example of a comparison that doesn't tell us anything. Anyway, so that's the idea of the comparison test. We'll be getting some practice on this in class. Please do not worry about that. I will make sure we have plenty of practice with this idea. But again, that is the major idea of this section, and there you have it. See you in class.